Okay, next topic is of ratio of instrument transformers. This is very important. This question will be asking in the exam for 6 or 4 marks question. Okay, here the first one is in terms of a ratio, that is actual ratio, that is taken as R. Okay, the actual transformer ratio is defined as the ratio of the magnitude of the actual primary phasor to the corresponding magnitude of the actual secondary phasor. Magnitude of the actual primary phasor to the secondary phasor in terms of the magnitude we are telling. Okay, that is taken as R is going to be equals to magnitude of R is going to be taken as magnitude of actual primary current divided by magnitude of actual secondary current in terms of a current transformer, and R is going to be defined in terms of a potential transformer as magnitude of the actual primary voltage to the magnitude of actual secondary voltage. This actual ratio is also called as the transformation ratio. In the exam, if they asked write about define for the transformation ratio or else the actual ratio, means you have to write the same. Then the second is of nominal ratio, that is represented as Kn. The nominal ratio is defined as the ratio of rated primary quantity to the rated secondary quantity. Either it may be in terms of current or voltage. Then therefore Kn is going to be defined as rated primary current to the rated secondary current in terms of a CT, and Kn is going to be equals to rated primary voltage to the rated secondary voltage, that is in terms of your PT. Okay, that is about the nominal ratio. Next is of turns ratio, that is turns ratio is taken as n, small n is going to be number of turns in the secondary winding to the number of turns of the primary winding, that is in terms of a current transformer, and n is going to be equals to number of turns of primary winding to the number of turns of the secondary winding in terms of your PT. We learnt about the actual ratio, S, then about nominal ratio, then about turns ratio. This is very important. It's a repeated question in the exam for 6 marks or else 4 marks, depends on the question paper. Then ratio correction factor, it is ratio transformation, that is actual ratio to the nominal ratio. Therefore RCF is going to be taken as R divided by Kn. Therefore R is going to be taken as RCF into Kn. The ratio which is indicated on the nameplate of the transformer is always it's of a nominal ratio. When you are going to use check your transformers, the ratio what it is given, it is always the nominal ratio only. Okay. Then next topic is of burden of an instrument transformer. When it is going to be taken, the over that when it is going to be occurring, that's what the meaning. Okay, just we go through here. The nominal ratio of an instrument transformer does not remain constant. The nominal ratio what we are defined, that is rated primary current to the rated secondary current. Okay, what it's actual, right? It's not going to be in the constant value. In practice, as the load on the secondary changes, the load it's always changing, right? For that reason it changes because of the effect of secondary current, and also power factor and magnetizing, as well as the core loss. We come across these losses, right, of the current, and this causes the error in the measurements. For the particular class of transformers, the specific loading at the rated secondary winding voltage is specified such that the errors do not exceed the limits. In standard transformers, if I am going for whatever its secondary winding voltage, those are in a specified manner, and the error what is going to be occurring, it is in a limited fashion. Okay, such a permissible load, such a permissible load is called as the burden of an instrument transformer. That change, it should be a minimum changes, it has to happen. If it is only with a limited fashion means it's okay, but over of that you'll be getting large errors. Okay, thus the permissible load across the secondary winding expressed in terms of a volt amperes at the rated secondary winding voltage or current such that errors do not exceed the limits is called burden of an instrument transformers. This is what the meaning of burden of instrument transformers. Therefore, the total secondary winding in terms of a burden, it's going to be taken as secondary winding induced voltage, that is square, divided by total impedance of the secondary circuit including load and winding. Total impedance of secondary circuit including load and winding, that is going to be taken as secondary winding of the current in terms of it. Here we define in terms of a voltage, now it is in terms of current. Secondary winding current square into total impedance of secondary circuit including load and winding, including load and winding. This is what the equation. If only the impedance of the load is considered, if only impedance of the load is going to be taken, then the burden due to only load can be obtained as secondary winding burden due to the load is going to be taken as equation secondary winding induced voltage square divided by impedance of the load on secondary, and in terms of current, secondary winding current square into impedance of the load on the secondary. This is what the equation in terms of a burden. Okay. Next is a characteristic of current transformers. The characteristics are going to be, the first one is taken as effect of power factor of the secondary circuit due to the secondary circuit. The power factor of the secondary circuit depends on the power factor of the burden on the secondary. This directly affects the two errors. We already come across the errors, that is ratio errors, phase angle. The ratio error for all the inductive loads, delta is positive. Hence, sin delta plus alpha is positive. Hence, the actual ratio R is always greater than the turns ratio. Due to ratio errors, that is delta is positive. Because of this, our ratio error is going to be greater than the turns ratio, that is N. R is always greater than N. For the capacitive burdens, R is going to be in the negative and R, that is actual ratio R, is less than the turns ratio. That is about in the ratio errors. Next, about the phase angle error. When load is inductive, the delta is small positive, then theta is positive, but as delta approaches the 90 degree, as a load becomes the highly inductive. Observe here, load is going to be acting as a highly inductive, then theta is going to be in the negative. Theta becomes the negative value. Positive it is there, but it's changing the phase. It is going to be in the negative. For capacitive loads, theta is negative and delta is negative and theta is always positive for the capacitive load. That's about the power factor of secondary circuit. Effects of power factor of secondary circuit. Next, effect of change in IP, primary current. The IP and IS, primary current and secondary currents, are directly related to the, as IP changes, primary current if changes means secondary current also it's going to be changing. For low values of IP, I naught is dominating, thus IM and IC are also dominating parts of the IP, thus errors are higher. Due to this, errors are going to be in a higher value. As IP increases, part of I naught becomes significant from IP, primary current. Hence, the IC and IM also are less significant compared to the IP. That is about IS, thus errors are less. Main compensating itself in terms of your currents. That's what the effects of change in the IP. Then effect of change in the burden or secondary. The secondary winding circuit burden increases means the volt ampere rating increases. Burden increases means volt ampere rating is also going to be increasing. Due to increased secondary current, the secondary flux increases, which induces the more voltage on the secondary. Current increases, flux increases, and also our voltage is also going to be inducing in the secondary. Thus, both IM and IC increases. To keep flux constant, IM and IC are going to be increases to keep the flux constant. Due to this, errors are also going to be increasing. Thus, more secondary burdens means more errors. Means the load what you are going to fix for your circuit should be low, or else what it is necessary, that much load you have to put on those. Next is of effect of change in frequency. If frequency is increased at a constant voltage, then the flux and flux density increases. Thus, there is a reduction in IM and IC, and hence errors also gets reduced. This is a normal, it's a simplest one. If the frequency is increased means at constant voltage, then flux and flux density are going to be decreased. Thus, reduction in the currents are going to occur. Therefore, errors are going to be reduced. These are the characteristics. This will be asking in as 4 marks only. Okay. Just you have to remember the highlights of these. Only 4 effects. Okay. Then, the errors which are occurring due to potential transformers are going to be taken as percentage of ratio errors is going to be given as Kn minus R divided by R into 100, and phase angle error is going to be taken as theta radians. It's not having any derivation, okay? Just you remember the equation. Then characteristics of potential transformers. The first one is of effect of power factor for secondary circuit. It's almost same to the previous one what we taken. The power factor of secondary circuit depends on the power factor of the secondary burden. As power factor decreases, angle delta increases. Then this, due to change in the delta, IP shift towards the I naught as seen from the phasor diagram. So we are not going for checking of those, okay? VP and VS becomes the almost in phase. Primary voltage and secondary voltage almost in the in phase, with EP and ES, EMF due to the primary and to the secondary respectively. Thus, VP becomes more compared to the EP, but as VP is constant, primary voltage is constant as supply voltage, the result is reduction in the EMF of the primary. Similarly, the voltage Vs also reduces compared to the ES. Hence, R is going to be increases as Vs decreases. Observe here, our actual ratio is going to be increasing as Vs decreases. due to decrease in the power factor of the secondary circuit. While Vs advances in phase and Vp retards, hence negative phase angle reduces as lagging power factor of the secondary decreases. Just remember this one you have to remember, it's a main. Actual ratio is going to be increasing as Vs decreases due to the decrease in the power factor of the secondary circuit. That is about effect of power factor of the secondary circuit. Next, effect of change in the burden on secondary. The change in the burden on secondary changes the secondary current and secondary voltage. Okay, as the secondary current increases, primary current increases. Secondary current increases means primary current also is going to be increasing. This increases the various drops. For constant Vp and Vs decreases. This increases the transformation ratio R. Thus, ratio error increases as the secondary current. Observe here, ratio error is going to be increasing as the secondary current, that is about the burden, increases. Due to the increased voltage drop, Vp advances while Vs retards in phase. Thus, the phase angle between Vp and Vs increases, becomes more negative as secondary current increases. This values of voltages is going to be increasing and values more negative values for the secondary current increases. That's what the about your burden. Okay, burden should be in a limited fashion. That's what the meaning. If it is increasing, again our turns ratio is going on increasing. That's what the meaning. Next above is of change, effect of change in the frequency. The same thing what we taken previously. If the frequency increased at constant voltage, then the flux and flux density is decreasing. Yes, this reduces the value of Im, Ic and also about the I0. This tends to reduce the errors, but increase in the frequency increases the leakage reactance. Observe here, increase in the frequency increases the leakage reactance, increasing the voltage drop. Increases the voltage drop. This increases the, due to this again, ratio and ratio errors. It's going to be increased. Thus, effects are opposite to each other. What is the effects are going for? It is opposite to each other. And the reluctance effect, resultant effect depends on relative values of I0 and also about leakage reactance. This is very important. Main effect is depends on the I0 and also about the leakage reactance. While the phase angle increases due to the increasing leakage reactance as well as decrease in the I0. As phase angle increases due to the increase in the leakage reactance and decrease in the I0. That's what the meaning. Next, effect on the primary voltage. The primary voltage is practically constant and there is hardly any significant change in it. Hence, there is no significant change in the error. Means the primary voltage, what it's changing, it's not affecting in a larger fashion. It's a small effects. In a constant way, it's going to be occurring. That's about the primary voltage. These are all about the characteristics of a potential transformers. This is also, it will be asking for 4 marks. Okay. Next, this is important. It may ask for 5 to 6 marks. That is reduction of errors in instrument transformers. The first one is of reducing the core loss and magnetizing components of the I naught. This we know what are the errors are going to be occurring. It's due to the core loss and also of the magnetization, right? We have to, if we reduce those, of course our what are the errors are there occurring due to this, we can reduce of those. In this, the equations of ratio and phase angle errors show that error depends on the core loss and magnetization. We learnt of this, right? Magnetizing components of no load current, that is I naught, and following precautions it has to be taken so that I can reduce my currents, that is IC and IM. What you have to do to reduce the values of these? Just first one, we have to go for choosing the low reductance core. Then second one is of the using the materials of high permeability. Yes. Then providing the smaller magnetic paths for the flux to the flux. Then next using the large cross section area of the core. And next keeping flux density in the core to low value. Flux density should be in a lower value. Then last one is of taking suitable precautions while designing the assembly and interleaving the course, the construction what you are going for, how you the design, how you will be going to take for the transformers. That should be keep in mind so that we can reduce the errors of the core loss and also about the magnetization. These are all the 6 methods we have to keep in mind while designing of the instrument transformers. Then about the reduction of resistance and leakage reactance. That's what we learned, right? How it is going to be done? The errors depends on the voltage drops, which are in turn depends on the values of resistance and leakage reactance. Then the resistance can be reduced by increasing the cross section of the conductors. The resistance how I can reduce? Just by increasing the cross section of the conductors and decreasing the length of the mean turn. Length of the mean turn. That's what the two things we have to remember when we are going to reduce the resistance. Okay, this is the one method. Then how we can reduce the leakage reactance? The leakage reactance depends on the leakage fluxes. Thus mutual coupling between the windings must be high, that is M value, right? Mutual coupling between the windings must be high, hence windings must be as close as possible. The windings what we are going to turn for the transformers, it should be very close. Okay, similarly keeping flux density as high as practical. Flux density should be high. Therefore, the number of turns required are less, hence leakage reactance are going to be reduced. This is what how we are going for. The only thing when you are going for winding should be very close and tightly it has to be connected when you are going for the transformers, so that your flux density should be high. Due to that your leakage reactance is going to be reducing. These are the two methods we are going to use in the transformers so that I can reduce my resistance and also about the leakage reactance. Then next is of providing the turns compensation. Turns compensation we can do for the potential transformers. R is going to be taken as N plus Is divided by N into RLE cos delta plus XLE sin delta plus IC RP plus IM into XP divided by Vs. Actually, these derivations are not there for your syllabus. You just go through these equations. And at no load, secondary current Is is going to be 0. Therefore, R is going to be equals to N plus IC into RP plus IM into XP divided by Vs. Thus, on no load, actual ratio is going to be exceeded by how many times? Of these many times. That is IC RP plus IM into XP divided by VS. The remedy for this is to reduce the primary turns. Reduce the primary turns or increasing the number of secondary turns. What we have to do? Either we can reduce the primary turns or else increase the number of secondary turns. Okay. Thus, for one particular value of the load, the actual ratio can be made equal to the nominal ratio. For one certain load, what you are going to apply, based on that load, we can make that our actual ratio is going to be equals to the nominal ratio. This reduces the ratio errors over the entire range of the burden when we do this. Okay, and this is called as the turns compensation. This is very important. Separately it will be asking for 4 marks. However, the turns compensation does not affect the phase angle. That's what the main thing. Turns compensation, it's not going to be affecting for the phase angle. Therefore, for the current transformers, the approximate expression for R is going to be taken as R is going to be equals to N plus IC divided by IS. Remember this equation. This is about the turns compensation. Then, thus the actual ratio becomes more than the nominal ratio. So, turns ratio is going to be reduced by reducing the secondary winding turns. Turns ratio is going to be reduced by the secondary winding turns. This makes actual transformer ratio equal to the nominal ratio. Turns ratio, it's going to be reduced by reducing the secondary winding. When it is done, our actual transformation ratio is going to be equals to the nominal ratio. This is called as the turns compensation for the current transformer. This is how we are going for. Next, what are the advantages and disadvantages? First, we go with the advantages. The normal range this is important again for 5 marks. Okay, the first point is of the normal range voltmeter and ammeter can be used along with these transformers to measure the high voltage and currents. From the transformers, it is easy to find the high voltages and currents. That's one point. The second one is the rating of low range meters can be fixed irrespective of the value of high voltage or current to be measured. A small range voltmeters also we can connect. Then these transformers isolate the measurement from high voltage and current circuits. We can measure of those. Okay, this ensures the safety, that is very important, safety of the operator, and makes the handling of the equipments very easy and safe. That's what the main importance of our transformers. Then, and these transformers can be used for operating many types of protecting devices such as relays or pilot lights. Different when we are going to use in a power systems, we can use of our transformers. And the last one is of several instruments can be fed economically by using of a single transformers. This is about the fifth one. And one disadvantage is of these instrument transformers is that they can be used only for the AC circuits. That's what the main, and it's not going to be used for the DC circuits. That's the main disadvantage of the instrument transformers. Only one disadvantage of the IT. Okay, these are things about today's class.